Okay, so the focus of this video will be what is this gravitational force? And this is important because we're going to distinguish between two different key terms that often get confused and get switched when talking about one. Okay, so if you remember from kind of middle school science, mass is the amount of matter in an object. Okay, now we will redefine mass here in a couple videos. Okay, but for right now, we're just going to take that old physical science definition by saying mass is just how much matter an object has. Okay, again, it is measured in kilograms. Now, remember, in physics, we use the MKS system, right? So MKS metric system, where this, right, is our unit for mass. So anytime you have something that is not mass, or that is not kilograms, make sure that you convert. The only time that you don't have to is when you, is if you know in the end the mass is ultimately going to cancel out, because the ratio of 1,000, if it's in grams, like 1,000 to 1,000 is the same no matter what. Now, one thing to keep in mind, that mass does not change wherever you are in the universe, right? So it's going to remain the same, right? So if I'm, 80 kilograms here on Earth, I'm 80 kilograms on the moon, 80 kilograms on Alpha Centauri, and so forth, right? So it's universal. Now, the opposite side of that, or the other part to this kind of conversation, is weight. So weight is the measurement of the pull of an object by a gravitational field. Now, so it does change. So it changes depending on where you are located in the universe. Okay, so some planets have a greater gravitational pull, some planets don't. So basically, essentially what is happening is, if I have an object located above the Earth, at this point in time, right, we have this gravitational field that surrounds the Earth directed towards the center of the Earth. Okay, so I get a little too close to the scroll bar here. Okay. So no matter where we are, all the objects are going to get pulled towards the Earth, right? So they're going to get accelerated downward towards that Earth. But the interesting thing is, from the center, the Earth is actually, let me do that in a different color. Probably yellow is better for this. So if the Earth will be accelerated up towards that object, but as you can see, you don't see that acceleration because the mass of the Earth is much more massive than is much greater than the mass of the object. Okay, so that's why we don't see that acceleration, because you remember or later we'll talk about Newton's third law. Okay, all objects essentially exert the same force on each other. Okay, now the question is, do we see that acceleration between an object, in Earth's gravitational pull? We will not see the Earth's acceleration towards it because of the fact that, visually you can see the arrow, right? That vector arrow is inside the Earth, whereas it's outside the object. Okay. Now we do have a formula to calculate the weight. So we abbreviated F sub G, and we'll talk more about this here in a second. Okay. Is equal to m times g, right? So really what happens at this point in time, before we get into the difference between the different types of forces, okay, we can also talk about what is called the gravitational field strength. Okay, and the gravitational field strength is just basically how strong is that gravitational field at that particular location, okay, and it's a vector. So yes, before we talked about acceleration due to gravity being lowercase g, but when you see it written like this as a vector, they're typically looking at the gravitational field strength. So that means at this location, right, Earth has a certain gravitational field strength, and it is based on the location. Okay, and we'll talk about that when we talk about Newton's universal law of gravitation. Okay, but so this is the gravitational field strength formula, and yes, they are the same formula. Okay, the only difference is one is looking for how much gravitational pull is there at a particular moment, and then when you see it written like this is the weight of an object. So when you go to the doctor and they tell you your weight in pounds, they're actually telling you how much force you're experiencing at that location. Okay, they're not telling you your mass. Okay, so when they convert it on their scale, right, and they say, okay, you have a weight of this many kilograms, they're actually using that term incorrectly because they're telling you your mass. Now, here in the United States, our equivalent to kilograms, or our measure of mass, I just found this out last week, okay, is the slug, okay, and where one slug is approximately 32 pounds, right? It's very similar to the stone measurement that they use I've seen it mostly in Ireland, but in the United Kingdom, they like to use the stones, okay? So here's a quick example of using this formula for weight. Okay, this says if I have 3 books in my backpack, a 2 kilogram, a 3 kilogram, and a 1 kilogram book, how much does my backpack weigh on Earth? And if I bring my backpack to the moon where the gravitational field is 1/6 that of Earth, how much will it weigh? Okay, so we're gonna kind of ignore the mass of the backpack, right? So we're just gonna really figure out how much does the book weigh? And so we're gonna use our formula, but because we're looking for the total weight, okay, I'm just going to call this mass total, which means then I'm going to do, right, so I've got 2 kilograms, 3 kilograms, and 1 kilogram, okay. Now to make, our calculation a little bit easier, we'll use 10, but remember you can also use 9.8, right, and you're going to have to go with whatever the AP test is asking you to do at that point, especially if it's a multiple choice question. They will use, most of the time they'll use 10, but if it's a free response, they'll actually say use G equal to 9.8 or 9.81. Okay, so if we're just using 10, we're going to find that we have a backpack that weighs 60 newtons. Okay, and we haven't talked about really what the unit for weight is or what the unit for force is, or which is what weight is. Okay, so newtons is the unit for force. All right, it's Newton's, named in honor of Sir Isaac Newton. Okay. Now, what would the backpack weigh on the moon? Right. So you have a couple options here. You can figure out what the G value on the moon is by simply doing 10 times 1/6. Okay, which ends up being 1.67. Okay, so you can see, like, when you watch those videos of the astronauts on the moon, they're kind of bouncing around because they feel less gravitational pull towards the moon. Okay, so that's one way you can do this problem, or the second part of this. So you have a total of 6, right, kilograms worth of backpack, and multiply it by 1.67. Grab my calculator real quick. So we do 6 times 1.67. You're going to get 10.0 newtons. So you can see on the moon we weigh 1/6. And the other way is to actually just use that relationship. Okay, so this is one solution. It's always good to know if there are multiple solutions to a problem to do that. So if I know FG Earth, right, was 60 newtons, well, FG Moon is 1/6 of FG Earth, right? So we're going to just simply do 1/6 times 60, and there it is again. There's our 10 newtons, right, on the moon. So the weight of the backpack on the moon is 10 newtons. Okay. So now in the next video, we're going to talk about these 2 types of categories of forces, and now begin talking about specific forces that we will use throughout the year.